Hi everyone, welcome back. In this video, we will be talking about valence bond theory and hybridization of orbitals. So first, as we know that each electron from each atom of a covalent bond creates a bond orbital, and bond orbital involves hybridization of atomic orbitals. And just as a review, atomic orbitals are the orbitals that we talked about when we were writing out the electron configuration for each atoms. For example, a carbon atom has six um, valence electrons, which means that if we write it, it will be um, two. Um, it will be something like this 6, and then we would have a 2 on the 2s, a 1s, 2s, and then 2p. So this uh, is the atomic orbital, another atomic orbital, and 3 atomic orbitals. However, as we know that if we draw the Lewis structure, a carbon will have 4 bonding electrons. So since this suborbital is actually full, so it doesn't explain the fact that it actually has 4 bonding electrons, because a full orbital theoretically shouldn't participate in the bonding process. So the valence bond theory and the hybridization of orbitals attempt to explain this phenomenon. So how does that work? So let's say we have a sp3 hybridization, and this hybridization simply means that we are hybridizing or combining an s orbital and 3 p orbitals. And when we're talking about hybridization of orbitals, we're specifically referring to the valence shell of the atom. So for example, when we are talking about carbon, we would draw it, bottom up. So we would have 1s here, which is 1 up, 1 down, 2s, 1 up, 1 down, and 3 p's, 1 up and 2 up. So we have 2 half-filled orbitals right here. So if we want to combine 2 s orbitals and 3 p orbitals, we would combine these 4. And the hybridized orbitals would be somewhere in between the s and p orbitals. But since we have more p orbitals involved in the hybridization, so these 4 hybridized bond orbitals will be closer to the p. So we would have 4 sp3 hybridized orbitals. And we would distribute the 4 electrons originally in the valence shell into these 4 newly formed sp3 orbital. And this would explain a tetrahedral domain, electron domain, when carbon, let's say CH4. So for this molecule, since C has 4 valence electrons and H only has 1, then we would have a shape that looks like this. So we would have C with 4 single bonds connected to the 4 hydrogens. And if we draw it into a 3D plane, we would have a tetrahedral shape. Something like this. And this model right here explains how a carbon could bond to 4 hydrogen atoms. While this model right here cannot explain that fact, because these 2 atoms supposedly do not participate in the bonding process because it is already full. It is a full orbital. So by hybridizing these 4 orbitals together, we would form a 4 half-filled bond orbitals that could participate in the bonding process, which creates a tetrahedral shape. The next example we're going to look at would be sp2 hybridization for a carbon atom again. So for sp2 hybridization, we are combining one s orbital and two p orbitals. So we're going to still look at a carbon. So we would have, this time, we would just neglect the 1s orbital because it is irrelevant to this hybridization process. So we would have 2s and then 3 2p's and still 2 half-filled. And this time we're going to combine two 2p's orbitals and one 2s orbitals. So the hybridized orbitals will still be somewhere in between these two energy levels, and we would have a one unhybridized p orbitals that still stays on the original p level. So we have three sp2 hybridized bond orbitals and one 2p unhybridized orbital. So we have three half-filled hybridized orbital and one half-filled 2p orbital. So this would explain a trigonal planar shape or a trigonal planar electron domain geometry. So let's say C2H4. So if we draw our Lewis structure, it will be two C's as the central atom, and then it will be a double bond in between the two C's, and then single bonds to the hydrogen atoms. And if we draw it on the 3D plane, we will see that all of these atoms are actually on the plane. The shape around each carbon atom is actually a trigonal planar. And that explains how carbon can connect to 1, 2, and 3 bonds to other atoms, because it has 3 half-filled hybridized sp2 orbital. And this second bond is actually formed by this unhybridized 2p orbital. So we call this second bond, which is formed by the unhybridized p orbital, a pi bond, and the other single bonds are called a sigma bond. So the general pattern would be for all single bonds, it is a sigma bond. For a double bond, it would be a sigma bond plus a pi bond, whereas a triple bond would be a sigma bond plus 2 pi bonds. So that is how we would look at these two different kinds of bonds. So sigma bonds, for carbon, sigma bonds are formed by hybridized orbitals, and it is a single bond. And for pi bonds, that is formed by unhybridized p orbital. And lastly, we're going to look at sp hybridization. And this, as the name suggests, is when we combine or hybridize an s orbital and a p orbital. So still for carbon, we would have a 2s orbital right here and a 2p orbital right here. And when we hybridize them, we would have hybridize this one and this one, and we would put 2 here, so it would be 2 half-filled, and then we would have 2 unhybridized 2p orbitals. It's still 2 electrons. So for these this kind of hybridization model, we would use C2H2. So we would still have two C's as a central atom, single bond to the hydrogens, and then triple bond in the middle. And we can kind of see that each of these hybridized sp orbital contributes to the 2 single bonds of the 4 bonds stem from the carbon atom, and then these 2 unhybridized p orbital contributes to the triple bond structure right here. And we will see that this structure is actually a linear structure, linear shape. So that would be how the hybridization of orbitals works, and how the valence bond theory and the hybridization of orbitals attempt to explain the more a deeper understanding of covalent bonds. Thank you for watching, and I hope this video is helpful. See you in the next video.